Good day! Welcome to quantum mechanics. So let's proceed. Classical physics states that it predicts a precise trajectory for particles with precisely specified location and momenta at each instant and allows the translational, rotational, and vibrational modes of motion to be excited to any energy simply by controlling the forces that are applied. Leads to conclusions that it relates to everyday experience. Physicists agreed that lights behave like a wave and it is also behave like particles, which led to the development of quantum mechanics. It is a branch of physics that deals with the behavior of matter and light on the atomic and subatomic scale. It attempts to describe and account for the properties of molecules and atoms and their constituents such as electrons, protons, neutrons, and other more esoteric particles such as quarks and gluons. These properties include the interactions of the particles with one another and with electromagnetic radiation, namely light, X-rays, and gamma rays. Proof for the wave theory of light started to accumulate from about 1800. At around this point, Thomas Young revealed that the two evolving beams overlap as monochromatic light passes through a pair of slits, so that a fringe pattern emerges on a screen of alternately bright and dark bands. Planck's radiation law. Max Planck assumed that the radiation energy is emitted not constantly, but rather in discrete packets called quanta. The energy E of the quantum is related to the frequency B by E is equals to h times B, the quantity h now known as the Planck's constant. Einstein and the photoelectric effect. In 1905, Einstein extended Planck's hypothesis to explain the photoelectric effect, which is the emission of electrons by a metal surface when it is irradiated by light or more energetic photons. Bohr's atom theory. A major contribution to the subject was made by Niels Bohr of Denmark, who applied the quantum hypothesis to atomic spectra in 1913. As the radiation emitted consists of a sequence of distinct lines, the range of distinct wavelengths from gaseous atom is known as the line continuum. The wavelengths of the lines are characteristic and form patterns that are incredibly complex. Wave hypothesis. In 1924, de Broglie proposed that matter has wave as well as particle properties. He suggested that material particles can behave as waves and that their wavelength gamma is related to the linear momentum p of the particle by gamma is equals to h over p. The wave theory teaches us that group velocity of wave holds its energy. Schrödinger wave equation is a mathematical expression describing the energy and position of the electron in space and time, taking into account the matter wave nature of the electron inside an atom. He was driven by a statistical optical formulation in which where the wavelength is limited relative to the measurements of the appliance used. The straight line propagation of light rays can be obtained from wave motion. In quantum mechanics, we also have the electron spin, and Dirac proved that an electron has an additional quantum number ms. Paul Dirac is the author of the quantum theory of electrons, and before this was called the electron spin, it was the Dirac equation. Here it was discussed that the ms corresponds to the additional form or angular momentum ascribed to the spinning motion. Quantum mechanics has two types of angular momentum, the orbital and spin. This spin angular momentum is defined as the angular momentum about its center of mass coordinate. There's more to learn about quantum mechanics, and identical particles is one of them. Wave function is a variable quantity that mathematically describes the wave characteristics of a particle at a given point in a space and time. The value of a wave function of a particle is related to the probability of the particle being there at that time as introduced by Wolfgang Pauli, an Austrian physicist. Imagine that there are two bowling balls in a collision course. We would have no trouble in identifying the path of the balls before and after, or during the collision. Have you heard of tunneling? Is that also a topic in a quantum mechanics? Yes, it is. This quantum mechanical phenomenon is seen by moving particles that manage to pass from one side of a possible barrier to the other, although there is insufficient energy to pass over the center. This remarkable microscopic particle property plays a major role in understanding many physical processes, including the radioactive decay. One of the foundations of quantum mechanics is the Heisenberg uncertainty principle. States that there is a limit to the precision with which the position and the momentum of an object can be measured at the position at the same time. To simply explain this, states that what one may know about the quantum system has a fundamental limit. For instance, the more accurate one understands the position of a particle, the less one can understand its momentum and vice versa. Along with the Heisenberg uncertainty principle, the quantum electrodynamics, also known as QED, accounts for the behavior and interactions of electrons, positrons, and photons. It deals with the processes involving the creation of material particles from electromagnetic energy, and with the converse process in which a material particle and its antiparticle annihilate each other and produce energy. Now, I will discuss the interpretation of quantum mechanics. First is the hidden variables in quantum mechanics. The theory may tell precisely what the fraction will be, but it cannot predict which particular nuclei will decay. In quantum mechanics, the randomness is asserted to be absolutely fundamental. Some physicists rejected the notion that the nuclei were initially in the identical state. Next is the paradox of Einstein, Podolsky, and Rosen. EPR is about the interpretation of the state vectors or wave functions and employs the standard state vector reduction formalism. Separated systems as described by EPR have definite position and momentum values simultaneously. And last one is the measurement in quantum mechanics. Schrodinger's time-dependent wave equation is the equation for determining the way the wave function varies with the time for a given physical system and a given physical environment. According to the Schrodinger equation, the wave function varies in a strictly determinate way. Moving on, quantum mechanics has been enormously successful in explaining microscopic phenomena in all branches of physics. I will discuss the three phenomena. Decay of the kaon. The kaon was discovered in 1947 and is produced in high-energy collision between nuclei and other particles. It has zero electric charge and its mass is about one-half the mass of the proton. Fact, the kaon is uncharged. Quantum theory predicts the existence of an antiparticle with the same mass, decay product, and average lifetime. Cesium clock. The cesium clock is the most accurate type of clock yet developed. This device makes use of the transition between the spin states of the cesium nucleus and produces a frequency which is regular for establishing the time standard. Lastly, a quantum theory has been used to establish a voltage standard and proven to extraordinarily accurate and consistent from laboratory to laboratory. It relates voltage to frequency with a constant of proportionality that depends on the Planck constant h and the elementary charge E. And that ends our quantum mechanics discussion. I hope you all learned something new from me. See you on our next one. Bye!